Okay, so welcome to this first session of the fall of 2024. There will be two talks. The first one is by Taisia Morozova, and she's finishing her PhD in Uppsala University in Sweden. And she worked intensively with Ingemar Kai. Many of you know of him. Today she will give a lecture on the work that she did with Ingemar on performance analysis of a buffered cellular network. And you will see all the details of coverage, Shannon capacity, I suppose, and steady state analysis of these queues in cellular networks. So, Taisia, please.
Yeah, thank you, Francois. And first of all, thanks to everyone for coming here, especially those who live in Paris. It's a long way. A special thanks to Francois and Christina for organizing this, for inviting me here. So I really wanted for a long time I knew about your group. I really wanted to meet your group. So I'm quite happy to be here. And so for my talk today, I decided instead of, taking certain paper and go really into the details of this particular paper, I decided rather to summarize the results that we got over these years that I've been doing my PhD. So basically to explain the model in details, and then just summarize contributions and the main ideas without really going into technical details. And the name of my talk, I guess you can see, so it's going to be about a cellular network with a buffer, and we will look at the main performance metrics of this network and steady state analysis. So maybe before I get to the talk itself, I'm going to run through a short summary of what we're going to talk about. So I'll start with a basic definition or description of a general cellular network, which was our physical motivation and interpretation for our work. Then we will move to a mathematical part and define a mathematical model of such a network. And then we will look at the main performance metrics. So I'll talk about coverage probability and Shannon capacity. And then because our network actually has a buffer, which is quite an important feature of this work, so we will focus on the buffer as well, and we will analyze its distribution and its dynamics. And then we are going to use some properties of non-homogeneous Markov chains for doing this. And then in the end, if I have time, I will also briefly discuss some other performance metrics such as loss and latency. And then we will look at some numerical and simulation results. Yes, so we start with just a simple physical model of a cellular network. Maybe I should say that our results actually, they consider they can describe a wide class of stochastic networks. So it doesn't have to be cellular, I guess. You can also describe some biology networks with the cells. But I think for our work, our main motivation and our main physical interpretation was actual cellular networks. So let's focus on this one for now. And let's consider a simple example of cellular network. So we have a grid. In this grid, we have some cells, and then in each cell, we have an antenna. In our model, it's only one per cell. And then in each cell, you have an arbitrary number of users. So then the user in each cell, they connect to the antenna in the same cell, right? And then they handle the signals. And then the users might be, I guess, mobile phones, except for in our work, they're not moving. And antenna is just a normal antenna, I guess. And so then the users and antennas, they exchange the signals. And basically the transmissions happen, and that's we look at the network in a time slot, so over some time slots. And basically this is the main dynamics of the network that we're gonna discuss. Yes, so this was just a short introduction about actually what our model physically means. And maybe I would like to now do a short recap of some related works that have been done in this area, and when actually it started and how's it going now. So I think our main motivation for this work is the paper that Francois and Jeff Randers have written in 2011. So when I started my PhD, we didn't really have a clear topic, a clear model. So we were just searching through the literature maybe for a year. And then we did this until we came across this work, and somehow it was motivational for us, and we decided to actually use this as a basics, and then we use some of the approach presented in this work to generalize it to our model as well. So then another thing is, when we started working, I had some background in queuing theory, my supervisor had as well. So we wanted to kind of have a network with a buffer, So we wanted to have a network with a buffer, so that we can apply some queuing theory. So we were interested in looking at reliable networks. So this is why we came across this problem of latency reliability trade-offs, like if you should consider
Please, can you turn off your phone, please?
Okay, so like this, is it working? Okay, yeah. Thank you. Yes, so then there were also a few of the recent works that were done in this area, in this latency reliability trade-offs. So is it okay? Or yeah. Yeah, so there were some recent works done in this area, and I think they can be tracked back to the paper of Wartwit in 1993, where they used some fundamental queuing theory, I think, to describe a buffer. I'm not 100% sure it was like a cellular network, but yeah, I think it was some kind of related to this communication theory. And they did have a buffer there, and they described it using some queuing theory. So this was also one of our kind of motivations. Yes, and then, like I said, in this work, we partially adopt the approach presented in a paper by Francois and Jeffrey Andres, or I can say we extend the results to a more general model, or we look at like a bit different perspective of the models. Yeah, so this was like a quick recap of the related works. Okay, so now maybe I will talk a little bit about actually the model that we consider, and I think we should really highlight some of the crucial features. So it's a cellular network with a buffer, which we consider in a slotted discrete time. Then we have the base stations, and we have the users. And in order to model the allocations of base stations and the users, we are using closed one-point processes. It's also kind of, I think Francois and some other people from Sweden also, they did work in this back in the 90s and 2000s. So we kind of adapted this approach where you have a process and then the locations are independent, which was actually quite easy to do like a tractable model on this. So we are going to adopt this approach here as well. So we have a process for base station, which has intensity lambda1, and then we have a process of the users, which has intensity lambda0, and they are all independent. So then each transmitter, it has a buffer where that stores the signals that were not transmitted because maybe of interference or some other things. And I think the closest physical model here would be the TCP protocols because they embody the transmission policy. Yes, and then yeah, what else do we have? So the buffer is quite crucial in our analysis. What else do we have? We have a random source of the input data. So we say that each cell obtains a new signal with probability P. So this probability is the same for each slot, for each cell. So it's just you can say this is just like an average kind of, or if you like multiply P with like lambda0, that would be the average number of signals obtained in the network. Yes, so then how do we build up cells? How do we allocate the users and the base stations? We use the shortest distance association policy. So basically we say that the user always connects to the base station that is the closest to it. And I think there are some other policies as well. Like you can connect also to the one that gives you the stronger power. But in our work, we focus on the shortest distance association, which is actually, yes, so then how to do this from the mathematical perspective, it's really easy to do using the Voronoi diagram, which I guess you're familiar with, but maybe just like a really quick reminder of this. So the Voronoi cells work in such a way that if you have a cell and you have a base station inside the cell, so then the distance between the base station and any other point within the cell will be smaller than with any point outside the cell. So then this is really good because when you use this Voronoi diagram, you can really achieve your shortest distance association policy thing. And there are also some known results, I think, in this field, which you can use. Yes, so that's the way that we do the association between the users and the cells. Then what else? Basically, when we look at the network behavior, we don't really consider like the whole network at once with like interfering queues or cells, but we focus like on one cell. Doesn't really matter which one, just like one typical cell. And then the results that we get, we like generalize them for the whole network. So we average. So then you can also say that basically the results that we get, they apply to like a generic cell in the network. So regardless of the number, the locations, and so on. Yes, so then now let's talk a bit about what happens during one-time slot. So in the papers that we did, we actually consider both uplink and downlink traffic. So we have results for both, but for this work, for this talk, I decided to focus only on downlink. Because maybe you don't have enough time to go through both. And I think downlink is just simpler because it is in some cases more explicit. You can get more explicit results. So let's say we have a downlink traffic, meaning that the base stations are transmitting to the users. And then what happens in one-time slot? So let's say we have some base station and located at X. It transmits signals to the user, which we assume is located at the origin. Just like for simplicity, so it doesn't really change the analysis. And then the base station has a random signal power, so we use this relay phasing model. So we have an exponential signal power, which has the same distribution at each time slot. And then we also have the received power to account for the distance between the transmitter and the receiver. And this is A of x here is the attenuation function, which might look a bit different from how it normally looks because we have an additional parameter kappa here. I don't think this parameter has like a physical interpretation. So the main reason we put it into this function because we did not want to have singularity at 0. So we wanted to bound the function. And I know that sometimes people just put 1 here, I think instead of kappa, but we wanted to kind of have more control over like what happens in the network. So we actually kept that general. But I don't think this is actually very important for the rest of the talk. It's just like some specifics of the model. Yes, so this is our attenuation. So the rest is the same. You have the distance, right? And then if the distance is large, the signal loses its power really fast. Yes, so then what happens is, like I said, if the transmission has failed, then the signal is stored in the respective buffer. So basically, each base station has a buffer, and then the signal is stored in this buffer, and it's going to be retransmitted in the next slot. So let's say that each buffer has a capacity k, and in our works, we consider cases k0, which is basically no buffer, or pure loss model, k finite, and then k infinite. And so for each of this case, we get some results. Yes, and then another thing is if the signal is already in the buffer, it cannot be lost at all. So it's gonna the base station is gonna try to retransmit it just as many times as it needs to. So in this sense, we don't really limit the number of retransmissions in one signal. We only limit the capacity of the buffer, but not the number of retransmissions from the buffer. Yes, so then now I would like to highlight a feature of the network, which is really important and which makes the whole analysis really complicated, is the activity of cells. So in our model, the base stations can be in either of two states. They can be either active, for example, if they have a new signal, which happens with probability p, as I mentioned, or they might have a non-empty buffer. then they are considered active. If this is not the case, if they have nothing to transmit, then they basically are idle, so they don't contribute to the interference. So then, how do we define interference? Is general thing of treating interference as noise and having the signal-to-noise ratio. So we consider the interference as a sum of all the received powers from the rest of the cells, except for now we only account for the active cells. So this is why we have this additional indicator here. So then initially we started to work with this model, and I think it became a bit complex really fast. So what we wanted to do, we wanted to use some kind of like approximation or simplification of this formula. So what we do is we take this formula 1, and then we replace the indicator with its expectation. So basically, instead of actually accounting only for the active users, we account for all of them and then just multiply by the probability of activity. So we define additionally this Qn. This parameter is the probability that an average base station is active. And then we basically just replace the indicator here with this thing. So now we get a new formula, like an approximated interference formula, where we have this Qn. So now this Qn is the problem because now everything is going to depend on this Qn, and Qn depends on the time slot. So what we have is we have some non-homogeneity with respect of time. Yes, so this is the approximation of the interference. And yes, of course, when you use approximations, you lose some accuracy. So the results you get might not be exact, but at least you get a tractable model. And this is what we kind of thought when we did this. Yes, so then we define this general signal to interference plus noise ratio, right? So basically just how much of the signal power you have with respect to the interference and some additional noise. So sigma squared in this case, just some Gaussian noise, some constant. And then we say that the transmission is successful whenever this ratio exceeds some predefined bound t, right? And then we define the coverage probability. So the probability that this ratio exceeds the bound t, which means the transmission is going to be successful. So initially we define the coverage probability conditioning on the locations of our process, right? Yes, and then maybe I should stress again that this SNR depends on n because of the interference, and everything now depends on n. So initially we defined the coverage probability conditioning on the locations, but we simplify this further because what we do next is we actually take the expectation with respect to the locations, and we basically, so then there is no conditioning really left because we averaged over the cell. And then at the end, we end up with this kind of formula where we integrate over like our x, which is like the radial distance on this one on one cell. So then what happens after you basically integrate this is you get some formula which does not depend on locations of other base stations or on your current base station. So even if you take like a real network with like some fixed location, this is not going to matter in this analysis. Yes, so what we did in our works initially was we actually managed to obtain a closed form relation, or like kind of closed form relation of this formula. We used also some of the approach that Francois has in his paper with Andrews. We use some stochastic geometry and some, integration. So I'm gonna skip this part because it's quite technical, and I'm gonna move right to the part where we actually get the formula. So this is like an expression or representation of the coverage probability of a general cell. So it's not really a closed form, I guess, because there's an integral, which unfortunately we cannot compute analytically. But I think that this formula is still quite useful because you can do numerics, right? So it contains all of the parameters that you need. And if you're interested in the behavior of coverage probability with respect to some of these parameters, I think you can quite easily do this with this formula, and then you can like do some plots and see how the function behaves. And we also did some parameter reduction here for simplicity. So yeah, but actually there are some special cases in this work where this can be really simplified. For example, if you take the case when kappa is 0, so kappa was this parameter of attenuation function. So if you set kappa to 0, it would mean that we have the attenuation is not bounded, basically. And then if we have the sigma squared, this is like additional noise. So if you put both of these parameters to 0, we will get like a really simplified expression. I don't have a number, unfortunately, here. So this expression, which is quite good because in my talk, I'm going to come back to this case a couple of times. Although like our results, they apply for a general case, but I like this case because it's explicit and sometimes you can really get intuitive of why things are happening by considering this case at first. Yes, so this is basically the expression for the coverage probability, and then we also define the Shannon capacity, or like the channel capacity in terms of Shannon formula, the well-known formula with the logarithm. So when we define a Shannon capacity, we want to connect it to coverage probability, right? So first of all, we use the integral representation of the logarithm, so we can write it like this. And then we can just change the limits here and put an indicator. And then, so we have expectation here, and then we can put expectation inside the integral so that you will get expectation of this indicator. And basically, this is just the coverage probability, right? So we basically mainly we did this to have like a clear direct relation to coverage probability, which is also quite nice because this formula here, as long as you know the coverage probability, you can also compute the Shannon capacity, both numerically or maybe in some special case analytically. Yes, so then we discussed this main performance metrics, right? Coverage and capacity. The problem is that they all depend on Qn. So yeah, you can like set the values for the rest of the parameters, but you cannot compute it at the current form because they depend on Qn. So what we're gonna do next is we're going to show that Qn actually has a limit. So some limit Q star under certain conditions, so not always. But we will show that it has a limit, and because of this, all the stationary metrics of the system, they exist. So then they can be computed, actually. Yes, and so because the shape of Q star actually directly relates to the buffer and the buffer behavior, we are going to start with evaluating the buffer distribution and the buffer dynamics. Yeah, so now it's going to be maybe a little bit of Q in theory, but I think it's not that much, and I think the results here are quite intuitive. So how do we define the dynamics of the buffer? Okay, so first of all, let's consider the case when buffer has a finite capacity. So K is K is finite. And then let's define the two indicators. So one would be the indicator of successful transmission, Z, right? And then AN would be the indicator of an arrival. So the number of arrival, of course, it's just binomial, right? Because we can only have one per cell. And then, so the buffer size is like the accumulated number of signals in the buffer, right? So how do we define the buffer dynamics on the slot n? Well, it's whatever was there before. So Bn minus 1 plus all the arrivals that came and did not meet a full buffer, and minus all the departures, that successful transmissions. Yes, and then because the buffer is finite, we actually might experience some losses. And then the losses can be defined in a similar way. So as many losses as we had in the previous slot, plus all the arrivals that arrived and saw a full buffer, so that they were lost. Yes, and then for the further analysis, let's also define UN. That would be the conditional coverage probability. So basically the same coverage, just conditioning on the like busy probability. So in other words, UN would be the probability of successful transmission given that the cell is busy, so that it has something to transmit. Yes, so then if you think about the buffer process, what can happen between the two time slots? The buffer can either increase by 1, or it can decrease by 1, or it can stay the same, right? So in a sense, it's like a jump process, and we can actually define the jump probabilities. For upward jumps and for downward jumps, they actually come out pretty simply here, I would say, because when the upward jumps happens, well, we increase by 1 when we have an arrival and we did not transmit, right? Then we go to the buffer. Otherwise, if we did transmit and did not get any new arrival, the buffer decreases by 1, right? And then we also define the boundary values. So actually our process B is a jump process, and it's a type of birth-death kind of process. However, it's not a simple one, unfortunately, because the transition probabilities, they depend on Qn, so it's really time non-homogeneous. Yes, so then let's also define a matrix for the transition of the process. It's going to be like the 3-diagonal matrix because we will only have like 3 diagonals which are non-empty, right? So the main one, which represents when the state of the buffer is the same, and then the upper one for the increased, and then the lower one for the increased buffer. And then the elements of the matrix, they also come out quite easily from the jumps probabilities. Okay, so then let's discuss the dynamics of the buffer a bit further. First of all, let's define the probability of a busy link, which we called Q. So remember, it was just a probability that the link is that some cell is busy. So then it is actually quite simple to define it in this way. So it is busy whenever it has at least something, so either new arrival or buffer is non-empty, so it's actually quite convenient to define it in this way. So what we do next is was quite an interesting idea proposed by Ingemar, my supervisor. So what we do is we fix slot n, and then what we do is we consider some homogeneous Markov chain which has the same transition matrix Mn, but it is homogeneous. So we fix n, for fixed n, it's homogeneous. So for all the kind of time steps, it has the same transition matrix. And then because the buffer is finite, and because this Markov chain is it's a good one, so it's irreducible and aperiodic, which you can actually see by construction. We know that this Markov chain has a steady-state distribution, and we will call it nu n. Which satisfies this equation, so which has this transition matrix. Yes, and then actually because we know the type of the process, so it's like the birth-death type process, and we know the transition probabilities, we can actually identify the shape of the distribution. And we know that the distribution will given, given this matrix M, given the jump probabilities, the distribution is going to be geometric or like truncated weighted geometric distribution, and it will have the following form. So the form here might be a bit complicated, but I mean, it's just like something that follows from the theory of birth-death processes. It's not something we came up with, it just directly follows from this theory. So basically, there is a distribution and we can identify its shape, and it looks like this. It's, I think, the main point here. So maybe you can already guess what we're gonna do next. Now we're gonna use this distribution, which has this steady-state distribution. We are gonna use it to redefine our Qn. So now in the formula for Qn, we, instead of the probability of an empty buffer, we just substitute this empty probability from this new homogeneous chain. But what we actually need to know is the distribution pi, so the distribution of the buffer. And we recursively define Qn using this, our auxiliary distribution, so-called, and we define pi using the same matrix, Mn. Yes, and I think I already said that a few times, but basically Bn is a discrete time non-homogeneous Markov chain defined by the probability matrices Mn. Yes, so then what we have defined the things for the buffer. Now we need to actually see if this buffer is ergodic, if it has a steady-state distribution. And for this, we actually, I don't think there exists a lot of literature about non-homogeneous Markov chains, so we actually had to search a bit. So we found one of the books we found was the book of Brimo from 1999. And in this book, they give, I think without proof, but they do give the ergodicity condition for non-homogeneous chains. And apparently this condition looks like this. So if you're interested in ergodicity of a chain, you actually need to look at the matrices and see if you can have the following limit. So that involves some total variation distance, which I just remind you that it can be computed like this. It's just the distance of the elements. Yes, so basically this is the condition that we are now need to see if we have this fulfilled for our network. So the first, or like the main thing that we should do is we need to see if Qn actually has a limit. So this thing I'm going to state without a proof and maybe intuitively a comment about a little bit on the proof. So we actually state that for a given P, there exists a limit Q star for a given P, meaning it actually depends on P. Such that, so this Q star is a minimal solution of the equation Q equals f of Q, where f of Q has the following a little bit complicated form, but this form comes from this geometric kind of distribution. And yes, so this thing is maybe a little bit technical, but we used a quite simple analysis to prove this thing. So I'm not going to give the details, but I can just explain to you. So we have this function f, we have function f of q, and because of some properties of the coverage probability, which this function depends on, f of q is actually monotone. So it starts at p, and then it monotonously increasing, and then it reaches its maximum at 1. And then if you look at the derivatives, you can see that at some point there will be like there exists a point q at which actually this f of q crosses the diagonal line. So you will know for sure that at least one time you will have a solution for the equation q equals f of q, right? So it goes. Okay, maybe I don't have anything to draw on the board, but basically it's
Yeah,
oh, okay.
that's a good thing.
Thank you. Maybe you can draw here.
Yeah.
So like roughly speaking, we have this f of p here, which starts at p. Then here we have q. And then if you draw like a diagonal line here, and then the function will start here, and then if you look at the derivative, you see that it actually at some point it will cross the line here, and then at 1 it reaches its maximum here. So then this crossing actually it might happen more than once, I think, but we are only interested in the first time it happens because we might have a few solutions, but we choose always the minimal solution. And the minimal solution is actually the one where the first time it happens is what we call our Q star. So the proof was a little bit technical and general, but I think it mostly comes from the properties of the coverage probability, right? Because it's also monotone, and so it was some analysis involved here. But in any case, we managed to show this. So we actually now can state the lemma, which says that Qn has a limit. Which is nice because since Qn has a limit, we can now define all of these performance metrics which depend on Qn. We can define like a stationary version of them, which depend on Q star now. So we have this U star, and we can define M star with the transition matrix. Yes, and then what we actually need to show is we need to show that we have our matrix Mn and our matrix M star. What we really need to show is the convergence in norm, because actually the norm of the matrix is just like a supremum of the sum of the elements, right? And this is actually exactly the formula for the strong ergodicity that we needed to show. But I think it actually, this convergence follows from, well, because we have actually the limit of Q star. So then this holds for Qn's, and then it will also hold for the matrices. Yes, and then M star is actually the transition matrix of some Markov chain, which is ergodic again, because, you know, it's finite, it's again, periodic and irreducible. So then because this convergence holds, we can actually see that the strong ergodicity condition is also fulfilled. So this one, right? Yes, so which actually means that our initial Markov chain Bn is also ergodic, and it has a steady state distribution. So because of all of these arguments, we can finally state the distribution of our Markov chain. So it's going to be, again, a geometric distribution, which has the following form. This also follows from this birth, death type of processes, except for the zero probability, we use some kind of a simplified version, which comes from how we defined Q. So yeah, otherwise it's you can easily check the shape of pi just from the probabilities that from the distribution of this ergodic Markov chain, which was geometric. Yeah, so this was one of our main contributions in our first paper, because we managed to identify the distribution of this a bit complex Markov chain. And then I thought it would be fun to actually see numerically how fast does this converge. So we didn't really have a goal to analytically compute the convergence rate, but I was just interested how fast we can get this. So I did some numerics. And basically, this picture illustrates how does the Qn converge to Q star. So here the black line is we start with P, with Q0 equals P, because, on the very first time slot, we have no other activity except for the ones that comes from P. So it's just P. And then we use in our definition for Q, we start to recursively define it at each time slot, and then we define it one by one, and then at some point, you can notice that it doesn't change anymore, and then you might think that you actually get the limit. For this case, we actually had a theoretical limit, which is the black line here. So then you can see that at some point you will reach this limit. I think, so this was the case when the buffer had capacity of 10, and I think it took around 300 steps to get the convergence. When I say get the convergence, it's not maybe very precise. It's just when you visually see that it stops changing, maybe you can think that you get the convergence. Yes, and then that was for the finite buffer case. In this case, we will always have this solution because we have the maximum of FFQ is always 1. With the infinite buffer, it was a problem because we do not always have this. So, and for the infinite buffer case, maybe I will go to the special case when we have kappa 0, sigma squared 0 as well, because we can get some explicit things. So the main difference here is that we don't have losses in this case. So the buffer dynamics only consists of arrivals and departures. So then if you look at the buffer dynamics actually, and if we want to have a steady state, we will end up with this kind of equation at some point, because basically what we will have is we will have buffer n minus buffer n minus 1 equals to p minus the coverage probability, and then in steady state we want this to be 0. So this is kind of the bound equation we are left with, which basically shows that your input work has to balance with your departed work. So it has to be the same roughly. So then we get this equation, and in a special case when kappa is and sigma is 0, you can get some explicit things. So you will get some explicit expression for Q star, which looks like this. However, Q has to be less than 1, and this leads to another restriction on P. So P has to be less than some critical value, and in this case, it's just this simple fraction. Yes, and I think we, unfortunately, only for this simple case, we managed to get this condition in a closed form. Then I think there's some numerical results. So this is the probability Q star as a function of P, because it always depends on P, right? And so for the case when K is 0, which means we have no buffer, it just coincides with P. For the case when K is infinity, as you can see, it is only defined up to 1 point here, because this point is actually our P critical. And for the rest of the values, they defined for each P, and basically the higher K is, the higher Q is as well. And then this is, we can get the same for the coverage probability as well. So the same pattern. Yeah, okay, so this was the coverage probability. Maybe I will mention about capacity also a few things. So actually in our work, I think capacity was published in a different paper where we put like a full focus on capacity, but I'm not gonna go to many details now, maybe just like some brief results. So for the capacity, we have of course the same problem. So for the infinite case, for finite buffer case, we always have this solution. So we always have the steady state, but for infinite buffer is not the same. So we will have to have some p, some critical p. So basically, then what we say is, so we have the capacity that depends on t, on the threshold t. So what we do is we define like a t max, which is like the maximal t that we can get in the network, such that this equation has a solution q, which is in a range from p to 1, so it's in a correct range. Yes, and then basically the meaning of this t max is that it's just like your system works for any t less than t max, and then whenever it is not the case, so whenever you exceed t max, basically it means physically that the system cannot adapt to transmission demands anymore, so you will probably experience large delays and some other problems. So then what we do is we state the Shannon capacity for the three cases, when the buffer is 0, when the buffer is infinite, and when it is finite. So when the buffer is 0, we don't have to solve anything. So it's actually quite simple because then Q just becomes P. So we already have everything in steady state. For the case of the finite K, we will need to solve the equation first to get Q star, right? And then we need to integrate over this. And then for the no loss case, when the buffer is infinite, we actually have this kind of representation of the capacity, which depends on Tmax. So for example, how would you compute Tmax? For example, you will have in this simple case, you will have this kind of formula, which only works for t which are less than Tmax. So then Tmax is obtained by solving the equation Q equals to 1 with respect to Tmax. Unfortunately, this is the only case for which it is explicit. Yeah, otherwise you will have to solve it numerically. Yes, and then so another thing that we proposed in the second paper is so-called admissible region of capacity. So we wanted to, okay, so we have the capacity per cell, let's say, and then we have a traffic per cell. So the traffic per cell, for example, can be P multiplied by W. So I think I forgot maybe this. I mentioned this, but in our case, W is lambda 0 over lambda 1, which can be interpreted as the average number of users per cell. In our work, we call it bandwidth, but based on some discussions, I think maybe this is not a very right thing to call the bandwidth, although like there are some different interpretations of this. But what we wanted to see if this, for example, like when do we have the capacity which actually covers this incoming traffic? So then we just assume that, okay, let's have a new performance metric, which would be like this admissible range. And then we can say that the system works whenever Shannon capacity exceeds this kind of the system's throughput, which is the product of P and the bandwidth. And then we define like a set of the values P and V for which capacity is larger than them. And then we say that, okay, system works fine in this case. When the capacity can no longer cover this, it means we cannot adapt to traffic demands anymore. So this is like some numerical example. And here for the cases K equals 0, 1, and infinity. So this is the capacity function, and the red line is the rho. So this product of P and V and double V. So then basically we say that whenever we cross this diagonal line, then it means that, okay, now we cannot work anymore. So now capacity is not enough per cell, so the system will not work. That's the interpretation that we came up with. Yes, and unfortunately, this is the only numerical results that we got for the cases 0, 1, and infinity. Because it was quite demanding, like from the perspective of like software, to compute this because you have to do a lot of numerical computations of the integrals. I tried to get some results for the case when k was 2, but they were really not reliable. So unfortunately, we were quite limited by the resources, and we could not get the results for larger k. Yes, and do I have some time? Some more time? Yeah. Okay. Okay, now.
Yes, question after.
Okay. Yeah, good. Okay, maybe then really briefly I will comment about the other performance metrics. So about loss and delays in this kind of systems. So then we consider the case when the buffer is finite, because it's the only case when you have both delays and the losses, right? So then we can write again the dynamics of the buffer in the following way. So basically, you can think of this as what happens to the arrivals that come to the network. They either stored in the buffer, or they successfully transmitted right in the same slot, or they're lost. And this is exactly what the first formula shows. And then I think we can now apply law of large numbers here to get some convergence in mean. And also because buffer is finite, of course, we will have that buffer divided by n will converge to 0. And so then by the law of large numbers, we can get the convergence for the number of losses. And then we will get in the limit the stationary probability of the loss. And then maybe if we rewrite our recursion, then we can also see that actually the probability of loss is the same as the probability of buffer being full, which kind of confirms that losses are only occurring whenever the buffer is full, right? And then when we have a new arrival. And then for the latency, we used like a Little's formula. So we just use the formula, the average buffer divided by p. And then we modified this a little bit. So we wanted to have it in such a way that the delay, if the transmission is successful right away, then the delay is still 1 because it still required 1 slot to transmit. So this is why we have this one here. Otherwise, if it was not successful, we will have this kind of little formula, so which depends on the average buffer size, and the average buffer size also comes directly from this geometry distribution that we got. And there are some numerical results, I think. So there is the delay, then there is some loss probability, then there is Q star and average probability, or just for illustration. Yes, so, and then finally, I'd like to conclude this with some simulation results. Simulations are always nice because, first of all, we have some approximations here, then we have quite a complicated model. So I was interested in see how close is this if we simulate like a real system. So then I used some discrete event modeling, stochastic modeling, and then we got some performance metrics for this, but not all of them, because I think mainly we focused on coverage probability, delay, loss, and some metrics I think are just not relevant for simulation. For example, Shannon capacity, I don't think you can simulate it, or at least in the way that we were interested in. So here are some simulation results. This is the coverage probability as a function of SANR threshold. So, okay, I think we get quite close results. Then this is the Q star as a function of P. And then this is the average buffer size for the cases when we had a buffer of 1, 2, and 3. Okay, so in this case, it actually deviates quite a bit for the larger values of case. Maybe one interpretation here would be that for larger P, it deviates because maybe these values of P are not relevant in real networks because they're just too large and networks can't work anyway. And then the same for the losses, the loss probability. So the same problem here. For larger buffer size values, we actually get less accuracy and less coincidence. Yeah, maybe I can briefly mention the 2 extensions that we are currently working on. So one extension would be to generalize this approach for a multi-tier network. So when we have more than one class of base stations, actually, I think you can use almost the same approach with like a slight modification. And another work is the ergodicity analysis of the network when the users are heterogeneous. So each user has its own property, has its own P, has its own buffer, and the buffers are kind of interfering. So then we have like a multi-dimensional Markov chain that we want to analyze, and it gets really complex for higher dimensions. But that's what we are currently working on. Yeah, so there are some references here. And, yeah, that's all. Thank you for your attention.
Okay. More comment on the question. So, you do some field analysis of the Q, right? Because when you, when you replace Q by E of Q.
Oh yeah, that's that's something that you can call my field as well.
And when you replace the actual short noise or interference by its expectation,
yeah.
so you do sort of
yeah, you can do.
My observation is that in the real system, if you really have Poisson cloud antennas, there will be some aggregates with lots of where interference will be very big, and these Qs will be discriminated against in these cloud areas because interference will always be very big, and therefore in that case there will be Qs if you give a given P per antenna. There will be Qs somewhere, there will be a set of Qs in the space which will always be unstable.
Yeah.
In that sense, the midfield analysis is not representative of the fact that you replace the expectation of the actual interference by its expectation or some averaging is leading to something which is qualitatively. It's very interesting, but there is more analysis to do in the list, which we need to look at not doing the conditional by keeping the conditional expectation given the point process. Right?
Yes.
And this is, I think, the main thing which transform your analysis into real field, which lacks capturing the actual fluctuations. In infinite network, there will be Qs that will clog for sure, right? Which is not captured by this mean field.
Yeah, that's a totally fair point, and I think I was criticized for this also recently. So I understand this problem now, but we are now trying to maybe do some more things in this new networks. So I understand that this is maybe not very accurate in the sense that you have this like one stability condition for the whole network, and you will of course have some Qs which are unstable. But I mean, I think to some point it was like tractable model, so that and for some of the Qs it might work. So yeah, maybe this is not very practical, but this is totally a fair point. So yeah, we are trying to work with this also.
Yes, I think so. You entangle Qs and Shannon currency is very nice, right? Because then you get the threshold for which there exists a Q star. The Q star is really the archetype of the mean field type.
Yeah, exactly. Q star is exactly
type equation.
Yes.
And so entangling queuing and the information is very difficult. But in a sense, it does not fully capture what will happen in the real network, where the spatial fluctuation will.
Yes,
there will be bad regions and good regions. It's not captured by this.
Yeah, this is the problem. But I think when I did the simulations, for example, the simulations I did not use any approximations, so I just computed an interference as it was, and then we tried to but then we averaged still over like the cells, and then we compared the simulations. So I think some of them were quite close. But yeah, if you look at the buffers dynamics from simulations, you can clearly see that some of them are not stable.
Lots of questions. Yeah.
When you talk about loss, you consider the delay budget loss or the buffer loss, the buffer overflow.
So how do you mean exactly?
The loss, right?
Yeah.
So is it the buffer overflow?
Oh yes, exactly. So it's whenever the buffer is full, and then you have an arrival.
There can be another loss when the packet has a delay budget, and that gets violated. So that also, for instance, each packet say has a delay of 10 milliseconds. So if that gets overshooted, if the packet is not served by that time duration, then also the packet gets dropped.
Okay. So basically, you're suggesting to look at another like interpretation of loss. Yeah, this is also a fair point. I think this is more like practical. Yeah, this is something we are also thinking about now. Thank you. Yeah.
I have a question.
Yeah.
So, you have a question?
Yeah, there was some.
Yeah, okay.
I found your research topic is quite similar with my research topic during my PhD. It's or more or less exactly the same system model. And I also consider also the finite. So in this point that the S and NR will depend on the Q dynamic and Q dynamic inverse depend on the S and NR.
Yeah.
So in the end, you will have a stable state for both the coverage probability and the proportion of the intelligence base station, right? But for that moment, I can observe this thing in the simulation. So in the end, the proportion of interferences will goes to stable, and the proportion of the as the current probability will go to a stable point. So I did a strong assumption for this point, and similar as you, I calculated the stable probability when the Markov process has a stable point. So at that, I think you find some references related to this figure that it's based on the So I really want to know how to prove that your Markov
so you basically don't have to come to Okay, maybe if you have some time that you can discuss it a bit further. Because there are some references with like this birth death type of processes, but I think it mostly depends on the like shape of your coverage probability function. And like for some simple case, you can show that it's monotone, and then you can show that it's decreasing, and then the function is increasing. So basically, it just depends on this kind of shape of the function. But maybe we can discuss a little bit with you after the talk, maybe in more details. Yes, thank you for your question.
So there is another talk after. We ask the question. So if people have other questions, please you can contact Taisia. You have the email address on the screen. So thank you again. Now we move to the other. Yes.